So today we're going to be solving some AS level chemistry past papers from the topic of states of matter. In the previous videos as well, we solved a lot of past papers, and today as well, this was all done in the previous class. Today we are going to be starting from this question. So we're going to try and solve as many questions as possible to attain perfection, and I just recommend you guys to practice a lot of questions. Practice makes a man perfect. So let's get started. Keep your calculators with you during this chapter because there are going to be a lot of calculations involved. So let's start. The volume of a vessel is this. The good thing is we have the volumes in meter cube. That is what we need for the formula of PV equals to nRT. Next part says it contains pure argon at a pressure of this. We're given with the pressure in pascals. The units are very important because if you guys are using the formula PV equals to nRT, you can't plug in the values with the wrong units. You can't plug in your temperature. You can't plug in your temperature in degrees Celsius. That's going to be wrong. You have to put your temperature in Kelvin in this formula. So you have to be careful about the units. And at a temperature of 25 degrees Celsius, the units here are wrong. We have to convert it into Kelvin. Under these conditions, it can be assumed that argon behaves as ideal gas. You should always remember that if anything behaves as an ideal gas, if any gas behaves as an ideal gas, then it will always obey one formula, and the formula is simple. PV equals to nRT, pressure times volume equals to moles times the general gas constant R times T, which is the temperature. So an ideal gas obeys this gas equation. Okay, which mass of argon does it contain? Okay, so now we have to calculate the mass. Simply let's plug in the values into the formula. Pressure first is 1 into 10 raised to power 5. Volume is this is our volume, 1.2 into 10 raised to power negative 3. PV is done. Now let's plug in N we don't know the number of moles for the argon gas, but we do know some things about argon gas. We'll discuss it later on. First, let's put in the values that we are dead sure about, that they are not wrong. So N we don't know. R is going to be 8.31, that's a constant value, times T. Temperature is 25 degrees Celsius over here, so we have to convert it into Kelvin. To convert degrees Celsius into Kelvin, you add 273 to your degree Celsius value. So let's add 25 plus 273, it gives us 298 Kelvin. So times 298. So now we have to calculate the mass from this. First we'll calculate the moles, and from moles we're going to calculate the mass. Okay, so now let's make N the subject of the formula. 2 10 raised to power 5 into 1.2 into 10 raised to power negative 3 upon 8.31 into 298 equals to my number of moles. And you guys know one thing, that moles can be replaced by the thing mass over mR, because you know that moles always equals to your mass upon your mR. So instead of moles we can write mass upon mR. So instead of moles I'm gonna write mass upon mR. And what is the mR of my argon gas? What is the mR of argon? You guys should know it. It's in the periodic table. It's 40. 40 is the mR of argon gas. So instead of mR, we're going to write 40. Done with the mR. It's 39.9. So let's use exact values and not risk our grades. So where is argon gas? This is argon. So it's exactly 39.9. So let's use 39.9 instead of 40 because it needs to be accurate. This goes here, gets multiplied, and then we get the mass. So let's put the entire value on a calculator, which is 1 into 10 raised to power 5 multiplied by 1.2 into 10 raised to power negative 3 multiplied by the mR, which is going to be 39.9 upon 8.31, which is the general gas constant, into 298. And what do we get? We exactly get 1.933. grams. So it makes option B the correct answer. I hope you get this is the entire working involved in this question. It was a fairly easy question, fairly easy. Moving on. Which assumptions are made about an ideal gas? You should know that when a gas has negligible volume and no intermolecular forces, it's considered to be an ideal gas. Okay, so you should know these two things about ideal gas. Firstly, it has no intermolecular forces, it has zero intermolecular forces, and the second thing about ideal gases you guys must know is zero intermolecular forces and negligible volume. These are two most important things. The other things as well, but these are the two main things. No forces, no volume. Ideal gas contain molecules with no mass. Okay, that's not a statement. That's not part of the ideal gas statement. Stick towards what you guys have learned. No intermolecular forces, no intermolecular forces and negligible volume. These statements don't say that it has no mass. So that's the first one's gonna be incorrect. Second one says ideal gases contain molecules with no volume. Molecules with no volume. That's what we are saying, that ideal gas has no volume. That matches our statement. Ideal gases have no intermolecular forces. Yeah, they have no intermolecular forces, and the molecules, they don't have any volume. So making option 2 and 3 the correct one. So that's option number D. Okay, the next question states that the table shows properties of 4 solids held together by different types of bonding, which row correctly describes the properties of a solid with a giant covalent structure. So what we're discussing, we need to have a solid that has a giant covalent structure. So in giant covalent structures, what do we expect? We expect high melting and boiling points. And why is that? Because we have to break the strong covalent bonds. In giant structures, we have to break the strong covalent bonds. For example, I take the example of diamond. Okay, for instance, I say I'm dealing with diamond. What do I have to break in diamond? This is one carbon attached to 4 other carbon atoms. Okay, so look at this carbon atom attached to 4 other carbon atoms, first, second, third and fourth. And to melt diamond, you need to break these 4 covalent bonds. So when you're breaking the covalent bonds, you should know that these covalent bonds, they're very strong, very, very, very strong, making strong covalent bonds, making giant molecular structures, giving them high melting and boiling points. So melting boiling point is going to be high. Solubility in polar solvents, they're going to be insoluble even in polar solvents. Because what are polar solvents? Do you think what is a polar solvent? Yeah, water is a polar solvent. Because H2O. What do you mean by a polar solvent? You have oxygen, you have hydrogen like this attached to it. A polar solvent means you have partial positive on hydrogen and a partial negative on your oxygen. This water is a polar solvent because it has permanent dipoles. Hydrogen has the dipole positive, partial positive, and oxygen has a dipole partial negative. So if you are diamond to water, it's not going to dissolve. So even if you have these dipoles, giant molecular are not going to dissolve. Water is a polar solvent. A polar solvent is a solvent in which the atoms, they have these permanent dipoles. So that's a polar solvent. So it's going to be insoluble even in polar solvents. So which makes option A the correct option. Moving on to the next part, which says when an evacuated glass bulb of volume 200 cm cube is filled with a gas at 300 Kelvin, each statement, each word is very important, and 101 kilopascals, the mass of the bulb increases by 0.68 grams. Okay, initially there's a mass, there's an evacuated tube that has no mass. So initially we're dealing with no mass, and then we have a bulb, the volume is this, we filled it with a gas, we added some gas to it. This was the temperature, slightly above room temperature is 298 Kelvin, so it's slightly just 2 Kelvin above. And this was the pressure, and the mass increased by this. The gas obeys the ideal gas equation. This is very important. Even only if a gas obeys the ideal gas equation, only if it's a ideal gas, then we can use the formula PV equals to nRT on it. What is the identity of the gas? So it's simply what they're asking about. How do we know the identity of a gas? We need to find its MR. So how are we going to find the MR? Let's plug in the values. For pressure is in pascals. Pascals we have to take. Over here we're given in kilopascals. So how to convert kilopascals into pascals? You guys should know this thing by now. How to convert pascals into kilopascals. Kilopascals into pascals. So it's going to be 101 kilopascals. Just kilo is replaced by 10 raised to power 3 pascals. Okay, pressure done times volume is in cm cube. We have to convert it into meter cube. So to convert cm cube into meter cube, we multiply it by 10 raised to power negative 6. Just remember this thing, that if you have 500 dm cube, to convert it into meter cube, you multiply dm cube 500 multiplied by 10 raised to power negative 3. To convert dm cube into meter cube, you convert it for this conversion you multiply it by 10 raised to power negative 3. And to convert your cm cube into your meter cube, you multiply it by 10 raised to power negative 6. Okay? And to convert cm cube to dm cube, you multiply it by 10 raised to power negative 3. And to convert dm cube to meter cube, you multiply it by 10 raised to power negative 3. Just remember these conversions for your ideal gases. Remember these equations. Not equation, just conversions. Acha, PV equals to nRT. Acha. So now n is the number of moles, which can be replaced by moles equals to mass upon mR. Now multiplied by R, which is 8.31, multiplied by temperature, which is 300. We need to find the mR. We need to make mR the subject. We move mR on this side, and this entire equation, it comes below, okay, in position for mR. So now if you make mR the subject, mR equals to mass, let's replace the mass by the value that we are given with. This is the value for mass, 0.68 grams. 0.68 multiplied by 8.31 multiplied by 300 divided by 101 into 10 raised to power 3 multiplied by 200 into 10 raised to power negative 6. So let's calculate what the MR comes out to be. 0.68 mass हो गया, 8.31 general gas constant हो गया, 300 temperature हो गया, divided by 101 into 10 raised to power 3 is the pressure, multiplied by 200 into 10 raised to power negative 6, which is the volume, and it comes out to be 83.9. MR comes out to be 83.92. So now we have to find which gas has this MR. Go to the periodic table. 83, krypton. Krypton has this MR. See for yourself. It's 83.798, which is approximately 84. And this also comes out to be approximately 84. So it's going to be option number B, which is krypton gas. Okay, I hope you get it. Moving on. Element X requires strong heating to react with oxygen. Okay, element X reacts with chlorine to give a covalently bonded chloride. Okay, Covalently bonded chloride. So if you have a chloride that is covalently bonded to another atom, for instance X, you know one thing for sure: X is gonna be a non-metal. And how do you know it's gonna be a non-metal? Because look, chlorine makes a covalent bond with a non-metal, because if X was a metal, chlorine would simply accept an electron and there's gonna be an ionic bond between chlorine and a metal. So definitely X is gonna be a non-metal. So we cut out sodium and we cut out magnesium. Now we have two other things: phosphorus and silicon. And now we have to figure out that both forms covalently bonded chlorides. So now we have to look at the first statement, which says that element X requires strong heating to react with oxygen. So does silicon require strong heating or phosphorus requires strong heating? Think about it yourself. Silicon is a giant covalent structure. Silicon is a giant covalent structure, whereas phosphorus is a simple covalent structure. Simple covalent. So first you need to break the bonds in silicon, which are going to be strong covalent bonds. Then silicon will react with oxygen. So probably it's going to be silicon, because it requires strong heating to react with oxygen. I hope you guys get what I tried to say. Phosphorus will react instantly with oxygen. It would react, but silicon wouldn't, because when you have a giant covalent structure, it's very unreactive. This is silicon. It's a giant spreaded out covalent structure that you can't even imagine. That's how long it is. Okay. Now, which graph represents the variation of pressure and volume of a sample of an ideal gas at constant temperature? Pressure and volume of an ideal gas at constant temperature. You might have studied this in physics as well, that if you have a piston, like if you have two containers like this, okay, so this is your container 1, this is your container 2, and here you have a gas, okay, and these are the gas particles. So if you increase the pressure and you pull the piston downwards, you try to increase the pressure, you pull the piston downwards, what happens to your volume? Now let's move the piston downwards. So if I move the piston downwards, my volume decreases. Initially before the piston was moved downwards, this part was my volume. This was my volume. But once I pulled the piston downwards like this, now what's my volume? Now what's my new volume? This part is my volume. So my volume decreased from this to this when I increased the pressure. I applied pressure from the top, my pressure increased, my volume decreased. So when I increase the pressure, the volume decreases. So I know that there's a inverse relation between my pressure and volume. There's going to be an inverse relation. Pressure is going to be inversely proportional. So C for graph D, which shows inverse relation. Graph B shows a direct relation. Graph A shows a linear relation, a linear decreasing relation. It's a linear relation. It's not an inverse relation. This graph shows inverse relation. And this one again is a different type of relation. This is inverse relation graph, and you should learn it by heart, I think. Next part says each of the substance shown as gaseous, which substance is most likely to show ideal behavior in the conditions shown. For ideal behavior, what do you need? What kind of things should you have for ideal behavior? Firstly, you should have no intermolecular forces, and the second thing you should have no volume. How do you have no volume? I told you right now that to have negligible volume you need to increase pressure. Pressure and volume are inversely relations. If you need less volume, you need more if you need less volume, you need more pressure. And if you need negligible volume, you should have no volume. That means that you should have a low pressure. Because at low pressure, your volume is going to be very less. If you have a high pressure, what's going to happen? Your volume is going to become illegible. Your volume though volume decreases, but what's going to happen is that it's going to become illegible. If you compare over here, 4 particles are here. This is all free volume. So over here you can consider these 4 particles negligible. But over here, when you have more pressure, only this area has no volume. So over here you can't say that volume is negligible. At high pressures, the volume becomes illegible. The volume can be seen. It can be seen there are these 4 particles. You can't ignore the 4 particles here. But over here, when there is a lot of volume, you can ignore the 4 particles. Do you get me? So, though your volume decreases, but the thing is that it becomes illegible. If you condense the gases in your... leave it. That's going to be confusing for you guys. So, to have negligible volume, you should have extremely low pressure. So that gases stay away from each other. And if they're away from each other, you'll know that they have negligible volume. You can ignore their volume. Okay, next, no intermolecular force. You should have high temperatures for this, because as you increase the temperatures, molecules move away from each other, and when they move away, they break away the intermolecular forces. These are 2 molecules attached to each other. You increase pressure, what happens? You increase the temperature, they start to vibrate, and when they vibrate, the molecules, they move away, and that is what happens when you increase the temperature. So for an ideal gas, the 2 conditions are high temperature and low pressure. So temperature should be extremely high. So this should be the temperature, and the pressure should be extremely low. So this one's the lower pressure. It's going to be option number C. I hope you understood everything in today's video. Do consider subscribing to our channel, and that's going to mean a lot. And that's it for today's class. I hope you liked it. Bye-bye.